That's good.
Okay. Yeah.
Okay, right. So I shall try and be brief. This is actually a talk, it's an adaptation of the talk I gave at Ocean Sciences. So if you've seen that, there'll only be a few
Oops.
new slides.
Somehow it's self-advancing here. Sorry.
Oh, that's excellent. I think it's because you went to slideshow mode. Just try full screen mode instead.
Okay, let me preview, view, full screen. There we go. Okay.
Okay, that works. Great.
Yep.
Okay, so let's get straight to slide 2. A bit of context for why we developed OM4. Over 10 years ago, we GFTL had a series of models which we refer to as the CM2 era, where the CM2.1 workhorse model at 1 degree had been used for, by then, well over a decade. There were some higher resolution ocean components developed in the context of that CM2 model to explore the role of resolution and resolving ocean eddies. And so this is a series of models documented by Delworth and Griffiths. And what was basically the message was that obviously, maybe not obviously, but that mesoscale eddies in the ocean are an important part of how properties and heat are transported around within the ocean. So one of the results, though, was at the time perhaps disappointing, was that there was an intermediate resolution between the 1 degree and the 10th of a degree at 1/4 degree, in which there seemed to be an increase in heat uptake, a larger drift than with respect to the high resolution model. And the reasons for why this was happening were, so we say, somewhat speculative, even though people had good ideas at the time. And around the time that model was being run, Illicek et al. Actually analyzed that particular run and they concluded, and this wasn't a surprise to many, that the heat uptake and drift was largely spurious, i.e. due to numerical methods. But why that should be the case, be worse at 1/4 degree rather than at 1 degree or 10th degree, comes down to the fact that you're beginning to resolve the mesoscale features and you're getting eddying activity and a lot of tracer variance at grid scale. And this was also something that comes out of the story about spurious mixing that was started back in the 2000s with Griffith's paper and many analyses thereafter. So one of the problems we faced was that for CMIP6 era, this last decade, all we could afford was going to be the 1/4 degree resolution. And these earlier results from the CM2 era suggested this was not going to be a good resolution. So we kind of set up ourselves for either a major fail or a big challenge. So can we go to slide 3? Thank you. So just quickly, a brief laundry list of what we have in OM4. OM4 is the ice-ocean component of the couple models, CM4. Both of these models are published now. The OM4 configuration was literally developed in the context of CM4. We ran the ice-ocean model very few times, really only as sanity checks. We were focusing exclusively on the biases in the couple model. And so we emphasize this, and we actually mentioned this in the paper. It was almost a surprise that the solution that we get when we run the model in ice-ocean mode was as good as it is, because we literally did not tune anything for the ice-ocean mode. The model was developed and built and tuned specifically for the couple mode. On the other hand, it may not be a surprise if you acknowledge that the atmospheric model that we have is actually pretty good, and so in the sense that it reflects the real atmosphere, this is a commendation to them. The model is nominally eddy permitting. As I mentioned in the last slide, this is a resolution that allows grid scale energy because you're beginning to permit mesoscale activity. One of the challenges we faced when it came to working with the ESM, the Earth system model, was that even this model was too expensive for system modeling. So there is a 1/2 degree counterpart in which there is a parameterization of the mesoscale eddies using GM and a mesoscale eddy kinetic energy scheme. The 1/4 degree OM4, for the most part, does not have a parameterization of mesoscale eddies, although we had set out to actually include a dynamic scale aware parameterization, which using working ideas from Morty Janssen, but unfortunately we weren't able to actually get it to work to our satisfaction in time for the release of this model. The vertical physics is a lot of homegrown stuff as well. The EPPL is our surface boundary parameterization of surface-driven mixing, Weichel and Hallberg 2019. We have a variant of the Fox-Kemper mixed layer eddy restratification process. We have a shear-dependent mixing, which is due to Jackson et al. 2008, and then a suite of interior mixing schemes, including the internal wave-driven mixing by Samwise and Millet 2012. And then the bottom boundary layer scheme is due to Legg et al. And with a few innovations on top of that. So it's fairly vanilla in terms of what physics is inside the model, but the schemes are actually mostly homegrown. Okay, next slide, please. So one last comment about why the resolution. The previous workhorse model had been 1 degree for over a decade at that point. And it was a short study, internal study by John Dunn pointed out that we were literally unable to represent the strong boundary currents at 1 degree. And he found that going to either a half or a third was able to get very much stronger, tighter boundary currents. And this was enough encouragement for us to move the ESM towards our half degree, where we begin to resolve the boundary currents much better. And then at a quarter degree, we begin to permit these large eddies across many of the basins, and especially within, not necessarily at high latitudes, but in mid latitudes and equatorwood. And so we felt that resolving that extra little bit cost for getting some of the extra physics in there was worthwhile. So we now consider the half degree to be the sort of our coarse resolution, and that going backward from a half degree to 1 degree is something where you are losing some, even though the model is not eddying at half degree, you are gaining something that's very important, which is these laminar boundary currents. Okay, slide 5. So this is a summary of one of the main results in our model, that in the ice ocean configuration that we can show that, as was speculated and analyzed previously by in the Ilichak result for CM2 2.5, that there is a spurious mixing component to models which is especially large at this resolution of 1/4 degree. And so there's an experiment here where we ran the exact same configuration and simply changed the choice of coordinate generation within the same algorithm. So in the talks 2 weeks ago from Steve Griffiths, explaining how the Lagrangian remap algorithm works, and again today with Bob, we're able to use any any vertical coordinate we like, and the algorithms are literally, they can be absolutely arbitrary. But we chose to use a hybrid height coordinate, density coordinate approach inspired by HiCom. Although it's not exactly the same algorithm as HiCom, it's very much trying to be similar, follow the same spirit. And then we compare a configuration which, with this hybrid coordinate to a conventional flat geopotential surface, geopotential coordinate. And on the left there, you see a horizontal average Hofmüller plot of horizontally average temperature with depth and time. And you see this big red blotch, and that is basically heat uptake and large drift of orders over a degree per century, by the a half degree per century. And in comparison with the hybrid coordinate, we were able to get the drift pretty much close to 0. And for comparison, when we switched to the half degree resolution and stop resolving these large eddies, stop permitting these large eddies, a different kind of drift will return, and this forced us to consider parameterizing those eddies with GM, and you'll see that the half degree model there is drifting a lot less than the quarter degree model in Z coordinates, but nevertheless has some biases that we return. So this was the major result, that we're able to reduce the drift in this model simply by using a hybrid vertical coordinate. Slide 6. Just change my view. So this is, remember that this model is built in the context of a climate model. And we care very much about drift and heat uptake in the climate system, which the ocean is very much in control of. And so this is another way of looking at the previous result. So I'm showing here the comparison again between Z-star and hybrid coordinates. The Z-star results are the dashed blue line. And this is a model, on the right-hand side, I'm showing a plot of the change in ocean heat content measured in zettajoules, which are the units that Zano et al. Used for an estimate of the actual heat uptake in a reconstruction she did publish last year. And you'll see that the dashed blue line is kind of charging off the scale. It is a huge amount of heat being taken up by the ocean, and presumably because of just the spurious mixing due to the vertical coordinate. Whereas the solid blue line is the hybrid coordinate model that we used in the climate model, and you can see that the drift is very much less. So we were very pleased with ourselves that we'd actually been able to build a model with such a little drift, at least without spurious drift. But however, as you can see, there is a real drift in the ocean, and we had actually, if you in retrospect, should have actually been shooting to get that drift if we had the physics right and using realistic forcing. What we're showing here is repeat cycles of, in fact, I'm using JRA in these plots here. In the paper, we used JRA, the core forcing, core interannual forcing. And over these periods, each of these 60-year cycles, there should have been a small amount of heat uptake, but we had tuned the model, built a model that had none. So that was actually a mistake with respect to the observations. But one thing about this plot is it tries to reveal how important eddies are. If I do look at the orange solid line, that's the half-degree model with the parameterized eddies. And if I turn the parameterizations off, that switches over to the dashed orange line, and that change is almost as large as the spurious effect. You can see that the eddies are a huge heat uptake relative to the drift. You've got to get the eddies right if you actually want to get the ocean model heat uptake right. They play a large role. And another way of looking at that is when we doubled the resolution. When I say doubled, I mean refined the resolution by a factor of 2 to 1/8 of a degree. We find that the model starts to cool down. And we are still investigating this, but the presumption here is that we're actually resolving the eddies better, which makes them more efficient. And we may also be reducing what remaining spurious mixing there might be. And in doing so, we've allowed the ocean to take up less heat. And so clearly, the blue lines and the solid blue line and the solid orange lines are somewhat fortuitous tunings that happen to have no drift. We got the right answer potentially, or something close to the right answer, but probably for the wrong reasons. Okay, slide 7, please. So let me just remind myself what I wanted to say. I'm so sorry, I've forgotten what I put the slide up for. Yes, this is just an illustration, just a snapshot to show that what you gain at the different resolutions. So the half-degree model there in the bottom right is just showing how there is it's a non-eddying model with potentially resolving the boundary currents, which are mostly laminar, and just the switch from half-degree to quarter-degree permits eddies to be, or the large eddies to be resolved. And qualitatively, you'll see that between the quarter-degree and eighth degree, it'd be hard to discern the two models apart because they're both eddying pretty much as each other. And so there's a qualitative change when you go from half-degree to quarter-degree. And whether the benefit from going from quarter degree to eighth degree doesn't appear to be so obvious, and yet we saw that there is a change in the efficiency of the eddies as we do that, as we go to the next resolution. So let's jump to the next slide. So the next slide is the one which is slide 8. We're going to move to slide 8. So this is a result. This is something which we haven't yet published, and I think it's extremely it reveals the potential for building a model with such low drift. So this is a comparison again of the hybrid vertical coordinate between and the z coordinate. On the left, I've got the hybrid. In the middle, I have the z coordinate. And this is the 50-year trend in temperature in the top 2,000 meters, zonally averaged, of an interannual core forced run. And the differences between the two left panels are, I hope, obvious. There's some broad structures that look very similar. There's big blue spots, but there's this big warming in the thermocline around 500 and below. And then if you compare that to the right-hand panel, this is an estimate of the 50-year change in the real world. This is from Dirac and Riffle's where they looked at, I forget what the time period is, but it's a 50-year change in zonally averaged temperature. And what you see there is a blue spot, but it doesn't have the same structure as we see in the model here. And there's a large surface signature and not much happening below, say, 1,000, unlike in the middle plot there. So if you go to the next slide, slide 9, now comparing again to the same observations, because there is only one set of observations, the left-hand side, what we've done now is we've switched from the core forcing to the JRA 55DO data set. And now you'll see there's a lot more similarity between the model trend and the observations. And moreover, I'm now showing an 1/8 of a degree solution versus the 1/4 degree solution. And you'll see that there is very little change in this drift. And the blue spot has changed its structure. We're using the hybrid coordinate here, so we're not seeing this thermocline drift. And you'll see, I think, to my eye, there's a large similarity. A lot of the observational trend seems to be explained by this model. So this is really, really exciting, because it really helps. It means that from the point of view of, say, data assimilation and trying to fill in the gaps in terms of our observations using models, a model with such little drift actually looks like it can actually look like the changes in the ocean can actually be realized. So this is something we're very excited about. Okay. So the next, so I've shown you so far. I've shown you some very positive aspects of the model, but the model is, shall we say, far from perfect. The sort of incentive we had to start looking at hybrid coordinates was to try and tackle the spurious mixing problem. And associated with this was this idea that the isopycnal models of the previous generation were pretty good at getting deep and strong AMOC circulations. And this is here, the AMOC circulation, overturning circulation that we got in the OM4 1/4 degree solution. And we are, shall we say, disappointed. It's relatively strong, but it's pretty shallow. The zero line is at 3,000 meters, so separating NAW and AABW in the Atlantic. And so it's quite shallow, and we were disappointed in this. And this is actually something that we are still working on. We're still trying to figure out exactly what went wrong here. We believe that there's a mixture of physics, as I'll show on the next slide, and also choice of coordinate, but we don't know that yet until we've actually managed to get the AMOC back to where we would like it to be. So on the next, so this is just showing a time series of AMOC, so there is a certain amount of periodicity, but the structure was unfortunate in the vertical. So if you're on the next slide, this is actually in the paper where we tried to analyze what might be going wrong, and we found that in fact we had set our interior mixing and our bottom boundary layer mixing to be incredibly strong. And this was something that we basically overlooked when we had examined overflows and the bottom boundary mixing and the consequence of overflows early on in the process, and had developed them to actually get the right depth for Mediterranean overflow water in the Atlantic. But subsequent changes were not, let's say we lost track of these properties in the subsequent changes, and ended up, we think, mixing away some of the Denmark overflow water with the explicit mixing. We have since then, and I haven't got any results to show this yet because there's still ongoing work, we have since then fixed the configuration to have not so strong bottom boundary layer mixing, and it does help a little bit, but it's far from enough. So this is still an open issue, how to actually explain and fix the depth of AMOC in this configuration. But we are working on it, and we will be releasing a newer version of OM4 when we're done. Okay, so let me just summarize. So on the next slide, on to slide 12, I'm done. Hopefully in a short enough amount of time. So we think OM4 is a step forward. It's a step forward for us for tackling making statements and tackling and modeling ocean heat uptake. We acknowledge that the configuration is imperfect. We made some mistakes in it. We have issues that we are trying to address still. But nevertheless, it's something that we think is going to be very useful for at least in the work in our context of climate studies. We are also planning a hierarchy of finer resolution models to continue to investigate the role of eddies and try and improve and understand how ocean heat uptake is controlled by the ocean. Okay, that's it.
Thanks, Alistair. Okay, we have Time for, oh, Peter Gent, first up. Go ahead, Peter.
So, Alistair, so in the tracer equations in the quarter of a degree, you have absolutely zero on the right-hand side, no eddy, no ready term?
There is no eddy, there is no, yes, there is no eddy in the sense of GM, and there is no ready in the sense of stirring, correct. So we're revisiting that. Multi-Janssen thinks we should be using some. Scott Backerman thinks we should be doing something. We have not gone far with it yet, but that is definitely something that needs to be addressed, I think.
But there must be a little diffusion to control noise, which must be then in your advection scheme. So
absolutely.
how
The
advection scheme is.
Right. So as Bob mentioned, we're using a third order, quasi third order reconstructions, meaning you have a second order advection scheme. There is numerical mixing associated with transport, but in the interior where we're tracking isopycnals for the coordinate, that mixing is mostly adiabatic. So if you mix a front end temperature along an isopycnal, it doesn't actually cause a diabatic transfer of heat. So by virtue of following isopycnals in the interior, we don't have rejection of that numerical mixing into the interior, but it does nevertheless smooth out gradients, along the coordinates. That argument, of course, means that we do have diapycnal mixing due to advection wherever we're using z coordinates up in the upper ocean, but there's so much mixing there anyway. The rationale is it doesn't matter. This is an issue we have, to investigate further, whether we need to use higher order schemes for the tracer advection, whether it matters to these solutions. We don't know the answer to those yet.
So when you say hybrid, you're more like Z in the boundary layer, and then much more like isopycnal in the deeper ocean. Yes,
and the goal is to be isopycnal as much as you can be, but it's actually very hard to construct this. And in fact, this is work we're working with Alan Adcroft and Eric Chazanier to try and import their vertical grid generator to improve on what we did. What we did was a very straightforward hybridization, and the HiCom crowd had learned quite a long time ago that you need to be a bit more sophisticated than the way we did it. So there's we think room for improvement in the coordinate generation. And we're finding when we've had Brandon Weichel, for example, has been analyzing what's been going on in the operation, and we are finding that there are sensitivities to how we determine the vertical coordinate at the base of the mixed layer and in the upper thermocline. So this is really a work in progress, I would say. There is lots to be improved here.
Okay, thanks.
Thanks. Gökhan, you were next.
Yeah, Alistair, as you know, we have been exchanging about these results, but I'm not confused again. How do you define what you mean by spurious? Because I felt like you are using it both to refer to numerical artificial spurious mixing and also improper and perhaps incorrect representation of mesoscale impacts in the solutions. Are you distinguishing the two, or?
I think it's a very good point, and perhaps we shouldn't distinguish. I have in my mind, we have in our minds thought about it as spurious due to numerics, but whether if you are having some sort of aliasing effect or diffusion due to eddy activity going on at the grid scale. It is all spurious. So spurious is a very general, all-encompassing word here.
So you're also referring to essentially missing physics or incomplete physics as spurious as well, I guess. That's what.
Well, or even perhaps mistuned physics. I mean, it could be that you got the right physics, but you might have chosen. So, I mean, when I write the word spurious normally, I'm thinking about numerical only. But you've just given me cover for anything that's wrong with the model. Thank you.
Okay.
Okay, Mehmet, I'm guessing this might be a follow-up. Go ahead.
Yeah, in fact, I think you almost said, Alistair. One question is, how does your AMOC look like in the Z-star simulation of quarter degree, which is very shallow in the hybrid coordinate? And the second one is, I mean, in a sense, how do you know it's only spurious is the key between those two heat uptake? How about your mistuned, or you are very well tuned your permutations for the hybrid coordinates, and now suddenly you try to Z-star, it might not work.
Yeah. So, well, to the latter question first, I think that a good handle on whether you've got spurious in terms of mistuning can be obtained by looking at sensitivities to parameters, and we haven't yet found a sensitivity due to by changing a parameter that just simply changes the depth of AMOC. So there's something else going on here. I think the answer to your first question about comparison to Z-star, it was also shallow in Z-star. Although we're having to backtrack through our figures to figure out when this happened, because it at one point was deep, and we're trying to figure out when that what's changed. We haven't put it in the we didn't publish those results, but we can we do have them on hand. So the Z-star model also had a shallow AMOC, and in fact was slightly weaker than the isopignal model. Sorry, the hybrid coordinate model.
Okay, Bill Large, I saw your hand up briefly. Did you have a question?
Yes, and I didn't put it down. Somebody did. Yeah, Alistair, my impression from your global heat uptake is you have enough parameter tuning to hit anything you want. Okay. Correct.
Can I come before you get to the? Before you get to your question? Can I come?
Yeah, you can do what you want. So
well, let me just comment on that quickly. We had no we took away a load of parameters from ourselves by taking any tuning of EPPL off the table, because we let Brandon Weichel tune EPPL only against single column LES models.
Yeah,
so
but that's not my question. So
okay, go ahead.
It was following. Given that maybe one of the things we as a whole community and all the people talking could work more on to what kind of metrics and observation should we be trying to fit. And certainly global measures like that are not, going to help us with parameter choices. They're going to have to be more basin-wide, and I don't know what that is, but that's another topic we could probably start to work on. Even your global average heat uptake, yeah, you got a blue blob, but it's the wrong side of the equator. If you take a look at your plot.
Yeah, I know.
So,
I just said, look at it with blurred eyes and it looks good.
Yeah. Well, he had cross-eyed. So I think maybe something we should think about is some of these observations or metrics, things we try and then communicate when we find sensitivities. Like you just mentioned, what the heck is the depth of the AMOC sensitive to? Well, somebody might know something here and not over there. So some idea when we get these metrics of communicating parameters that have some sensitivity to that would be maybe save a lot of duplication of efforts and stuff like that.
Yeah, good idea. I mean, I think we would all agree with the sentiment. Of course, we actually have to do it. It's like,
yeah, I know.
It takes time to these things, right?
Okay, Steve Yeager.
Alistair, I wanted to ask about what we should actually expect when we are forcing with core or JRA GOGO in terms of long-term ocean heat uptake, given that these forcing data sets have been purposely normalized to have zero net heat flux into the ocean when coupled to observed SST. So if your model was perfect, it should show no net warming over the time period of the forcing.
So I think that definitely is true for core. I'm not sure that's true for JRA.
That is true for JRA.
It is true for JRA. That's designed to do that, yeah.
Okay, well then that probably explains why we have no drift in those two when we use those data sets. But yeah, it's a good question. So that's interesting because we're seeing the trend within the 60-year cycle. We're seeing the trend that we want to see, as I showed. It's a challenging problem. I mean, we don't have the proper feedback on the ocean warming on the fluxes. So actually, I don't really know, Steve. Honestly, I don't know how to answer this. I think we've had a repeated cyclic conversation at GFGL, and I think it's spanned a few of you as well, about the value in repeat cycle forcing of in these experiments. what does it mean to run a model that should have force, a heat uptake or a drift, and then resetting it back to the beginning? If it has indeed been adjusted to have no net forcing, which I didn't appreciate in JRA, then maybe that's more viable. But there are still these kind of discontinuities, and there are trends in the model that we think are real. So it's kind of reconciling that with the idea that we shouldn't have any drift is hard to do. So I don't know how to answer it. I mean, it is a bit of I'm a bit confused about it, to be honest.
Okay, I'm not seeing any other hands raised. I think we've gone 2 hours, but if the speakers are willing to stay on, if people have questions for either Bob or Alper, we could entertain those now.
Yes, happy to stay on.
Bill Large, you're up again.
Well, it goes back a bit to Bob's talk where he said there's no more CFL problem with the in the vertical. So one of the questions that comes to mind is what is determining the highest resolution you can have, or your shallowest first level? Can it be a meter, half meter, or what is determining it now? Because if we start to work on that problem, one could conceivably start to get SSTs that are more like SSTs, and it might be something to think about. How far could you push that? I assume
So,
yeah.
Okay, sorry, go ahead.
No, go ahead. You answer that's what is determining it now.
So right now it is coupled instabilities. We assume that there's no feedback of the surface heat fluxes on the surface properties over the course of a time step. And so if you take a piston velocity, basically a linearization of your bulk formula, or however you want to get at it, times a coupling time step, that says your vertical resolution has to be something of order half a meter. If we included that implicit feedback within the ocean calculation, we think we could make it much smaller than that. In other words,
so that would get you most of the way there, and I think might be something to think about. Would the vertical coordinate, the layer coordinate, get into trouble if it's so thin that it goes unstable? Because right at the surface, you're unstable, right? If you're cooling. So would that be but that's pretty fine. So is that what would ultimately stop you, or can you have unstable layers?
Well, with EPBL, we don't seem to have too much of a problem with the unstable layers, because even though they're unstable, they're not a huge source of energy. And in fact, it's kind of a physical source of energy that, when you're cooling at the surface, you're driving convection. There's a release of potential energy.
Yeah.
Whether you reach the point where you had some kind of weird non-hydrostatic effects that you should be taken into account, I really don't know, but that's something where the parameterizations seem to do an awful lot of cleaning up of that sort of thing within the surface boundary layer. With the momentum equations, you would also want to make sure that you have parameterizations that are able to adjust and kind of work implicitly. That's one of the things I like about the Jackson et al. Scheme, is it's kind of an iterative and implicit solver. If you took the initial instabilities, shear instabilities in the surface, and treated them explicitly, it's possible that could give you troubles, but I don't have experience with that directly.
So
but it seems to be pretty robust to very fine resolutions at the surface.
So just to summarize, I mean, so there is a problem with resolution at the surface due to due to the missing the way the fluxes are done. But in the interior, we can handle very, very thin layers stably. So away from the forcing, we go to sub-millimeter regularly. So there is no lower limit if it wasn't for the forcing.
No, I think this is worth pursuing. It looks like we could get to a point where maybe all you have to do is a skin layer correction or something, and could really get what's going on during the day near the surface without I don't hear a showstopper anymore.
No, and in fact, that might be one of the nice things that you could use to calibrate how you're treating the surface boundary layer properties, because that magnitude of the diurnal cycle is something that is directly observable. It's something that doesn't depend so strongly on the horizontal fluxes the way the kind of deeper boundary layer stuff does. It actually might be worth pursuing and very interesting. I agree with you, Bill.
Okay, thanks. Dan Amrine.
I just had a couple of questions for Bob. The first, you talked about the need to do additional pseudo-compressibility passes, I think on kind of a regional basis. And I was wondering if that needed to be recalibrated potentially for other climates or certain applications of the model. And then the second question is about what tools are available to accelerate the equilibration of the model, for instance, tracer distribution.
Okay, so the first one, no, the model keeps track of how much mass has been able to move from one cell to another, and if there's more mass to be moved, there's basically, it keeps track of when it needs to do another pass. The number of passes that you need to do is kind of capped at the number of baroclinic dynamics steps, right? So if you're accumulating, it's just kind of the nature of the continuity solver. If you've only had 4 passes through the continuity steps, it's hard to see how you would have moved mass through more than 4 layers in even the most extreme case. And so you say, okay, well, if you had to do 4 iterations and do 4 steps, how are you saving anything? Well, the way that you're saving is that almost none of the ocean, you have to do so many steps. And in fact, in many cases, I suspect you're never actually having to take that many steps. Right, so that's self-adapting.
Okay.
On the second question of how do we accelerate, that's a good question. I think we have a talk coming up in the series in a couple of weeks about the use of Jacobian-free Newton-Krylov solvers as a way of accelerating things, and I'm looking forward to hearing it. At GFDL, the way we've done it is we've just run a long time. So we would be delighted if somebody could suggest things that work better. But the other part of it, and I think this is going back to Alistair's slides, where if you start off with a model with less drift, even though the intrinsic e-folding time scales of the water mass property are the same, if you start off closer, you have to go through fewer of those e-folding time scales before you get to within your tolerance of an acceptable drift rate. So I think that the drift in temperature that Alistair showed seems to help. But I mean, at the end of the day, if you're looking at tracer distributions in the deep Pacific, it's going to take a couple thousand years. It may actually be a bit more if you have a model with very weak diapicnal mixing. If you have a model with stronger mixing, then maybe that spurious mixing is actually helping you to equilibrate faster. And at the end of the day, I don't have good solutions, but I hope other people do.
Okay, thanks.
Okay, maybe one last question from Dr. Gent.
So I asked Steve this question last time, but I wanted to get Bob's answer, which is, how did you decide how frequently to do the vertical remapping? Because doesn't that set, in the end, the overall diffusion rate of some of the traces?
I don't think it does, because I think that the tracer diffusion is dominated by the along layer mixing, the advective mixing. I mean, I know that some people have done things like in NEMO, they'll have a Z-like model and they'll let it bounce up and down because they think a lot of the advection, the spurious mixing is set by vertical advection associated with gravity waves. I personally think it's dominated by a long layer advection and stirring, especially in places where there's a slope between your coordinate surfaces and isopycnals. And so in that case, I don't think that that time scale really has a lot to do with the magnitude of the vertical mixing. We do tend to try to restore towards, if it's a Z-like coordinate near the surface, we'd like to kind of keep the time scale shorter than about a day, because I think that the diurnal cycle and could give you some kind of weird aliasing. If you have Ekman pumping that's driving your top layers resolution deeper over the course of a day or something, that would be a bit weird. We've never really explored whether you could, how far you could push it, but that would be an interesting study.